Hello and welcome once again for another ES340 video. This is day 13, example problem 1. And so we're going to be dealing with entropies, and we're going to see how to read them off the table, the specific entropies here. So using the appropriate table, determine the indicated property for a process in which there is no change in specific entropy between state 1 and state 2. So to be clear, the wording here means that S1 has to be equal to S2 in all of these cases, A, B, C, D, E. So let's start with part A. So part A, it says water with P1 equal to 14.7 pound force per inch squared, with T1 equal to 500 degrees Fahrenheit. P2 is equal to 100 pound force per inch squared, and we're asked to find T2. Okay, so the first thing that we're going to obviously have to do is go to the tables. So let's do that. Let me see if I can pull up the tables here. Hopefully everything is working okay. Yep, here we go. Okay, and so here we are at the tables, I'm gonna, why not start with the saturated temperature table, because we're looking for temperature, easiest to start there. But if we go down, I just have to remind ourselves of what the values were here. It's gonna take a second to pull it back up, but we had a pressure of 14.7 and a temperature of 500 degrees Fahrenheit. So 14.7 and 500 degrees Fahrenheit. Well, let's look at our pressure here. If we come down, notice that at 14.7, which is right here, if I have a saturation pressure of 14.7, then the temperature, the saturation temperature, right? These are saturation temperatures, is 212, and our temperature was 500 degrees Fahrenheit. And so, just as a reminder, that means that we're above the saturation temperature, which implies, and I'm going to write that down here just so that we remember, just to remind ourselves about using the saturation temperature. This means that we should use the superheated table. It means we've lifted up outside of that curve, right? We're outside of the curve, the TV curve, for instance, therefore we're if I were to draw this, we should probably practice using the TS curve. It's very similar to the TV curve, and it just looks something like this. So for state 1, basically we're going to be like somewhere in here. We're in the superheated region. Okay, and this would be a temperature of 500 degrees Fahrenheit. Obviously, it's just a sketch, so we don't have to get it exactly or anything like that. So because it is superheated, then obviously the saturated tables no longer are useful, so we'll go to the superheated tables, which is A4E here in this case. And we were looking at a pressure of 14.7, which is right here. So 14.7 and a temperature of 500. So at 500, the pressure is 14.7. So I can just kind of come across here. And what am I looking for? I'm looking for S, lowercase s. This is in BTUs per pound degree R. And if you look over here, it's in the very last column. At pressure 14.7 here, and temperature 500, and that gives me 1.9263. So my S1 is going to be 1.9263 BTU per pound degree Fahrenheit. So S1 is equal to 1.9263 BTU per pound degree Rankine. Sorry, not Fahrenheit. Okay, so that's my value for S1. We noted that S1 is always going to be equal to S2 in these problems because of specifically the wording here of the problem. There's no change in the specific entropy. So that means that S2 also has to be 1.9263 BTU per pound degree Rankine. Okay, and then they gave us a new pressure, a higher pressure of 100 pound force per inch squared, and we want to find the temperature. So we know two things. Remember, we always need to know at least two properties, and sometimes the wording tells us the second property. Sometimes we just have both properties. In this case, we have both. We have P2, the pressure is 100 pound force per inch squared, and we have S2, right? We have two properties. Now now everything is completely specified in the case of a non-ideal gas. When we have ideal gases, we actually only need one property if it's an ideal gas, which is nice. But in this case, we need two. And remember, be careful of the wording, right? In this case, this particular case, it's not the wording that gave us the two properties. We just actually have the two properties. But sometimes, you know, they use wording like saturated. Well, the fact that it's saturated tells you what that second property is, right? Or maybe it's a mixture, and they give you the quality of the mixture. Again, that's enough to work backwards and find a second property or something like that. But we always have enough information to get the two properties. Okay, and so coming here, we have to go back to 100 pound force per inch squared. I'm going to go here. It will tell me what the it will give me an indication here if I can't possibly be in the superheated regime based on the value of S. Okay, if the value of S ended up coming in lower than any of the values listed on the superheated table, that would indicate that that we're in the saturated table, and we'd have to go back. But in this particular case, 1.92 being, remember that this last column here, it's way up here, is S. So it's the fourth column if we're looking here. I just passed 100. It's the fourth column, or yeah, fifth column, I guess. 1, 2, 3, 4, 5. It's the fifth column here. And notice that I have 1.6034 to start, 1.61. Obviously, I'm in the superheated regime still. Because I have my S2, my specific entropy in this case is 1.9263. So I'm going to scroll down, and at 1,000 I see 1.92, but it's not 1.9263, it's 1.9204, right? And then I see 1.9551. So that indicates to me I'm going to have to interpolate here to find the temperature. So notice that the two temperatures that I have to interpolate between are 1,000 degrees Fahrenheit and 1,100 degrees Fahrenheit. Those are my two temperatures, and my two specific entropy values are 1.9204 BTU per pound degree Rankine, and 1.9551 BTU per pound degree Rankine. So I will take a note of that. I have them written separately here, so I can go find that. So I'll just call them A and B. So TA was equal to 1000 Fahrenheit. TB was equal to 1100 degrees Fahrenheit. SA was equal to 1.9204 BTU per pound degree ranking, and SB was 1.9551 BTU per pound degree ranking. Okay, so now using the tables, obviously, I was able to find these values, and I need to interpolate. So I know that I want S2 to be 1.9263. So basically, when I do the interpolation equation, I'm going to say T2, it's going to be equal to M, which is the slope. We'll get the slope in a second here, times S2 minus SA. It could have been SB, but then the next part would have to be also TB. But in this case, I'm just going to use SA and TA. Okay, and then M is going to be equal to TB minus TA over SB minus SA. And again, it doesn't actually matter the ordering that I put those in, right? As long as the associated values are in the correct spot in the minus sign, and in both cases it's okay. So it doesn't matter which way I do that. And basically, if I substitute in these values, what I find, these values here, substitute them in to the equation, what I find is T2 is equal to about 1017 degrees Fahrenheit. So I found my property in that case. And by the way, that's also superheated, and look, the temperature is quite a bit higher. So if I were to come back here, state 2 would be, directly above and like somewhere up here. This is 1017 Fahrenheit, would be state 2, right? Both of them are in the superheated regime, and their S value has to be the same, so they should line up on the x-axis here. Okay, so now let's look at part B. Part B says we have water again, and the temperature is 10 degrees Celsius. It has a quality of 0.75. Okay, the quality of 0.75 immediately tells me I'm going to go to the saturated table, because that's where we find anything that's a mixture. We find mixtures on the saturated table. And if it's saturated, obviously, we find that on the saturated table. And actually, we use the saturated tables a lot, which is why typically I suggest going there first. When it's condensed, we tend to also use the saturated liquid value in that case. So, so keeping all of those things in mind, typically it will be the saturated table we have to go to, but you should obviously know when you have to go between saturated and superheated. In any case, okay, so we know these things. So again, I'm going to go look at the table. So let's go back to the tables. Basically, what I want is not the tables now, but is not the English value tables, but rather the non-English tables, the SI tables. So immediately we know we want saturated, and I just have to remind myself what we were looking at here. It's water, that's one thing, and we were given the temperature. So let's go to the temperature table, A2. Okay, and now what we're going to do is we're going to look for 10 degrees Celsius, which is right here, as you can see, quite close here. And we know that it's a mixture, so it's going to end up having to be somewhere in between these values. So in order to find that, again, we'll use, I'll take down these values, but look at 10 degrees Celsius, SF, the saturated liquid value, SF of entropy is 0.1510, and that's, the units are kilojoules per kilogram Kelvin. So it's 0.1510, and the saturated vapor value is 8.9008. So I'll take note of those values, and I will find what the actual value of S is, and then we can move on to find the desired quantity, which is actually the pressure in this case. Oh, sorry, yep, it's this one, but it's still the pressure. So we don't know what S1 even is at this point in this problem, so we're going to need to use this equation that we have for finding mixtures, which is the SF plus X, which is the quality, times SG minus SF. And that means that S1 is equal to, SF was equal to 0.1510 kilojoules per kilogram Kelvin, and SG was 8.9008 kilojoules per kilogram times Kelvin. And so, and we were given X as being 0.75. So substituting those in, we get 0.1510 plus, I'm not going to write the units, but the units will come out correctly, obviously, as long as I'm using the correct values here. 8.9008 minus 0.1510, and those are kilojoules per kilogram Kelvin, and what I end up getting is 6.7134 kilojoules per kilogram Kelvin, which means that S2 must be equal to 6.7134 kilojoules per kilogram Kelvin. That comes from the problem, right? The problem said that S1 has to be equal to S2. There's no change. So no change means from state 1 to state 2 means that the values of S are the same. Okay, so now what am I going to do? Well, I'm going to find the pressure. And to find the pressure, well, I was given a new temperature here, or I was given a new temperature, and the fact that this is saturated vapor at state 2, which also indicates to us what the pressure would have to be. So we're going to go to the pressure tables. Let's go to the pressure tables, because that's what we're looking for now. And basically what we're looking for is something that's between, it's saturated vapor, right? So I have to use the, it's saturated vapor, so what I have to use is the saturated vapor value. And if I come here all the way to the right-hand side almost, actually I can go all the way to the right-hand side because that also has the pressure, but the one right next to the pressure on the right-hand side of this table is the saturated vapor value, right? So remember I said that you always have enough information to give us you know, a pair of quantities, and that, and in this case, the fact that it's saturated vapor tells us something, and that's enough to get us to be able to figure out what the pressure would have to be. So I'm going to scroll down here and look for 6.7134, which was the value we know S2 is, but unfortunately, again, it's in between these two values. It's in between 6.76 and 6.708, right, for these two values. So that's my that's between a pressure of 6 and 7. So I'm going to have to interpolate now in order to find this. So I'll do this one last example of interpolation, and then I'll let you figure out how to do the interpolation again. Remind yourself for the next part. But basically what I'm going to say is, just like before, I'll write the equation in terms now of pressure. This is very similar to the temperature one, but now in terms of pressure here. And I know that M is going to be now equal to PB minus PA divided by SB minus SA. And what are all those values? Well, we read them off the table. PA was equal to 6 bar. PB was equal to 7 bar. SA, coming off of the table, was 6.76 kilojoules per kilogram times Kelvin. SB was equal to 6.708 kilojoules per kilogram times Kelvin. And if I substitute all these values into this equation up here, what I find is this is P2, by the way, my P2, which was what we were looking for, comes out to be about 6.896 bar, approximately. So that was the value that I was looking for there. And again, if I wanted to map this on my TS curve now, just as practice using the TS curve, again, the TS curve looks like the other curves that we've dealt with before. At 10 degrees Celsius, somewhere in here, it was at a quality of 0.75, right? And that was my S value. And then I need to draw this a little bit better because I didn't draw it nice enough here. So basically I'm going to want this to be on the curve now. If I go straight up. Then up here at the new temperature, whatever that is, I could have read it off the table. I didn't think about doing that. But up here at the new temperature, it's right on the saturated vapor part of the curve, right? This part up here, I was marking my critical point to be the top of the curve, and then this is state 2, this is state 1, okay? So that's what it would look like on the TS curve. Now, let's move on to part C. So part C says air is an ideal gas. So we're going to go to the air is an ideal gas table. And it's given a temperature of 27 degrees Celsius and a pressure of 1.5 bar. And we want to find what the new pressure is. So remember that there's something special about the ideal gas table, so let's actually go and look. We don't actually get S, right? We get S circle. So let me go back here. So I'm back here, and I see that I have ideal gas properties of air table, that's A22. So I'm going to go to A22. And the temperature was given to us in Celsius, which means that we have to convert to Kelvin. 27 degrees Celsius is about 300 Kelvin. I mean, you know, it's technically 300.15. We'll just drop the 0.15 and not worry about that. It's 300 Kelvin. So if I come down here, I see a temperature of 300 Kelvin, and I'm given S circle, right? This is not, look at the top of the table here. It says it has the little circle above it. S circle is not S. Okay, this was just our way of trying to get an estimate of the integral in our equation that we had before. So be mindful that S circle is not S, but that's 1.70203 kilojoules per kilogram Kelvin. And obviously our temperature was 300 Kelvin. And the question is what is the second pressure here? And I think we were given temperature 2. So we were given 127 degrees Celsius, yes. So T2 at 127 is 400 Kelvin. Okay, so we know we can go down here now to 400 Kelvin and we can get the second S circle. Let's keep going here. The second S circle, just make sure I'm in the right part here. It's 1, 2, 3, 4 over, right? 1, 2, 3, 4. So 400 Kelvin is 1, 2, 3, 4 is 1.99 194 kilojoules per kilogram Kelvin. So now I'm going to go back to here and write those quantities down. And you might say, wait a minute, how am I going to find pressure 2? Hold on a second, we'll get there. So let's write down what we have. We know that T1 was equal to 300 Kelvin. T2 was equal to 400 Kelvin. S1 circle was equal to 1.70203 kilojoules per kilogram times Kelvin. And S2 circle was equal to 1.9914 kilojoules per kilogram Kelvin. And remember our equation for ideal gas, right? So we had two of them. We had the incompressible version of these equations and the ideal gas version of the equations. Let's just keep those separated out. But for the ideal gas equation, we know that S2 minus S1, the change in S, has to be equal to, well, S star of T2 minus, not star, circle, sorry, S circle of T1, which is what we have here. That's what I mean by these S1 and S2 is of T1 and T2. Minus R times the natural log of P2 divided by P1. Okay, that was our equation. We have another one with the specific volume, right? We can deal with that as well. But this one is for the pressure. Now we know S1 is equal to S2 because that was what it said in the problem. So that means that this becomes 0 is equal to these things. S2 circle minus S1 circle minus R times the natural log of P2 over P1. We were also given P1, by the way, so we can deal with that. Which means that R times the natural log of P2 over P1 is equal to S2 circle minus S1 circle. The natural log of P2 over P1 is equal to S2 circle minus S1 circle divided by R. We're just doing some algebra now. And then I can obviously go take this to the e to the log P2 over P1 has to be equal to e to the S2 circle minus S1 circle over R. P2 over P1 is equal to e to the S2 circle minus S1 circle over R. And finally, because e to the log cancels each other out, right? P2, which is what we were looking for, is equal to P1 times e to the S2 circle minus S1 circle over R. And we are going to need the R value for air. And there's two ways that you can go about getting that. In this case, R is, I'm going to use this one just so that we can remind ourselves, R bar over M, capital M, where M is on table A1. I can find M for air, right? And R bar, of course, is the classic value that you know, 8.314 kilojoules per kilogram Kelvin. So if I do that, then I find that R, I'm not going to calculate it out at this point. We'll just leave it in terms of the value that we find off of that table. From table A1, we find M for air is 28.97, and now what we're going to do then is we're going to substitute in all the values. So we have S1 circle, we have S2 circle, P, I should probably write down what P1 is. P1 was 3 atmosphere, sorry, this one was the one above, 1.5 bar. So if I substitute those values in here, the R value here, the S1, S2 circles, I get P2 is equal to about 4.119 bar. Okay? Now let's see part D. I'm not going to go to the tables now. I'll just assume that you can go and find them on the tables yourself. T, what do we have? Again, air is an ideal gas. Now it's going to be the English tables, but again, you're looking for S circle here. We have T1 is 100 degrees Fahrenheit. We have the two pressures, and we want to find T2. So we're going to have to go to the tables, obviously. We know S1 is equal to S2 again. S1 equal to S2. So that means, again, just like in the equation up here, S2 minus S1 is 0. So we're going to be 0 equal to S2 circle minus S1 circle. And again, we have pressures here, so this will be useful. Minus R times the natural log of P2 divided by P1. P2, we were given both P2 and P1 in this case. P2 is equal to 2 atmospheres. P1 is 3 atmospheres. So that's going to be 2 atmospheres. P1 equal to 1 atmosphere. Sorry, 3 atmospheres. And if I look up the values on the table here, basically I'm not given S, I don't know what this one is, so I'm going to solve this for that. It's going to be S2 circle is equal to, because that will help me find the temperature going back to the table, is equal to S1 circle plus R times the natural log, in this case, of 2 divided by 3. The atmospheres will cancel each other out, so I'm not going to bother writing it. And we need to find R in terms of because for air, because in this case we're using English units, so we need the R in terms of English units, right? R is going to be equal to, again, R bar over M. And that one is going to be 1.986 divided by still 28.97, still the same the same ratio of units there. And S1 circle, if you go to the table at that temperature that was given at temperature 100 degrees Fahrenheit, what you find is S1 circle is equal to 0.60950. So if I do that out, I get S2 circle is equal to 0.5817 BTU per pound degree ranking. And what you'll find is this value sits in between a couple of values on the table for air. So you have to interpolate to find the temperature. So interpolating, I'm going to expect you to be able to do the interpolation. A22E we get that T2 is approximately 498.7 degrees Rankine, or 39 degrees Fahrenheit. Okay, and then finally for part E asks us refrigerant 134A, so we'll have to go to that particular table. And then it gives us T1 is equal to 20, P1 is equal to 5, P2 is equal to 1, and we're asked to find V2. That's interesting. So we know that, I'll just write down what we know. We know that T1 is equal to 20 degrees Celsius, P1 is equal to 5 bar, P2 is equal to 1 bar, and we want to find V2. So if we go to the table, what we find is that from A12, using that table, we find S1 equal to 0.9264 kilojoules per kilogram times Kelvin. That means that S2 has to be equal to 0.9264 kilojoules per kilogram Kelvin. And going back to the table, what we find is that going to table, we need to go to table A11 now that we know this. Because this one is a mixture at that value of S2, and we find that X, the quality of that mixture, is as follows. These are just values off of the table. Obviously, you should be able to recognize these values. 0.9395 minus 0.0678, and that's about 0.985. So it's pretty close to a vapor, to a pure vapor, but not quite. So V2 then is equal to VF plus X times VG minus VF. And again, if you substitute in the values that you find off the table, you find that this one comes out to be 0.188 meters cubed per kilogram. Okay, so that's how we use these tables in the case of entropy. Hope that is helpful, and see you again soon.